Existing skeleton-based human activity recognition attacks can be divided into white box and black box approaches. White box approaches require prior knowledge of the full details of a victim model. Black box approaches require numerous queries or the same training data of the victim model. All previous attack methods also rely heavily on data labels. Their settings of existing SHAR attacks are overly restrictive. To this end, we propose a new attack setting, the hard no-box attack, which requires neither access to the victim model nor to the labels. We train our model by contrastive learning. This unsupervised method learns skeleton features without labels, which is suitable in our attack setting. For hard no-box attack, we design a new no-box adversarial loss, propose novel skeleton motion-informed gradients and present a family of novel gradient-based attack strategies enabled by the new gradient. Since class labels are not available in hard no-box attacks, we utilize positive samples and negative samples for defining the adversarial loss. Motion manifold information has been ignored by existing gradient-based methods. The raw attack gradient assumes each frame is independent and does not consider motion dynamics. Therefore, we propose skeleton motion-informed gradient to capture motion manifold information. We propose the first-order SMI gradient by assuming the Markovian model to represent the motion dynamics. In our work, we choose to employ time-varying autoregressive models to compute the SMI gradients. We also propose the second-order SMI gradient by alternatively assuming autoregressive model for motion dynamics. For explicit gradient computation, we also use the time-varying autoregressive model. Our newly proposed SMI gradient can be combined with many original gradient-based methods. For example, IFGSM can be combined with SMI gradient and we call S1 IFGSM and S2 IFGSM. We can also obtain S1 MeFGSM and S2 MeFGSM by using SMI gradient in MeFGSM. We define a perceptual deviation indicator to evaluate the imperceptibility of adversarial skeletal samples. M is the number of adversarial samples. T is the total number of frames. L is the number of joints in the skeleton. Our perceptual deviation indicator considers the deviations of joint position, bone length and acceleration. We report the perceptual deviation of different attack strategies in no-box attacks with different budgets. Our method have better imperceptibility. We provide the results of IFGSM before and after using our proposed gradient. As highlighted by the red color, the neck of our motion is more natural. Our motion has a more smooth and realistic spine when compared with the IFGSM. In this comparison, the neck of the IFGSM motion is twisted. The IFGSM produces an unnatural spine while our method does not. In the process of standing up, the waist of the IFGSM motion is more twisted. We also compare the results of MeFGSM before and after using our proposed gradient. The spine of our motion is more realistic. The neck of the MeFGSM motion has a larger twisted angle and the change between the two frames is larger. By using our proposed gradient, our motion is more natural than the MeFGSM. In the process of standing up, the neck of our motion is more smooth and natural. We also report the fooling rate of attack strategies with target models on NTU dataset, where enter Greek is the global clipping strengths. As shown in table, our methods improve the fooling rate. We have proposed the first hard no-box attack on SHAR, proposed a new skeleton motion-informed gradient, and presented a family of new gradient-based attack strategies enabled by our SMI gradient.